How are you all doing this morning?
Good, how are you?
Doing well.
All right.
Let me try this again with the volume actually turned up so that I can hear you if you respond to me. How are you all doing this morning?
Doing all right.
Good deal. At least I noticed early this time that I had the volume turned off. All right, so today we are going to be working on the biasing circuit. So let me open up my library. And let's start with a schematic first. So I'm going to create a new cell and I'm going to call it a beta multiplier with a schematic. Okay. So give me just a moment to find that.
Did you ever figure out why it was giving you like the weird graph?
I did not. I didn't have a lot of time to work on it over this weekend, so that's on my to-do list for this afternoon while the seniors are taking their mock FE.
Gotcha.
I had an idea about why it might be doing it. I hope that I'm right, because if I'm not right, then I have no idea why it's behaving so poorly, but I'll figure that out. Let's see. Dun, dun, dun. There we go. All right, so I guess I'm just going to start on the left-hand side of the beta multiplier reference circuit, literally just straight out of the textbook. So let's go to the components, and we need a, making sure PMOS. And I'm just going to try to make it match the textbook pretty much exactly. So this guy is going to be labeled MSU2. It has a width of 10, a length of 100. Move the text up here. I'm going to need to set the spice level of it to, or spice model of it, excuse me, to PMOS. I'm just going to set that over here for now. Let's see. Then I'm going to have below that, let's see, I'm going to have a little bit of wire. So the gate and the drain for that MSU2 transistor are tied together. Now I'm going to do my NMOS that is directly below. This guy is going to need to be mirrored. Edit mirror, there we go. The drain of this is connected to that. This guy is a 10x2 NMOS labeled MSU1. I'm going to make sure to remember to set my spice model. And we'll drag this text out over here as well. And wire them up to ground. All right, then we have that NMOS transistor that's labeled MSU3 that the textbook says is going to be a 10 by 1, but we are going to make it a 20 by 2 because in our simulation file, like if we look at the C5 models.txt, it literally says 2 needs to be less than L drawn less than 500, and 10 needs to be less than W drawn is less than 10,000 with VDD is equal to 5 volts. So I don't think it will give us an error if we drew a 10 by 1, but the simulation would not be valid because we're explicitly told the length needs to be at least 2 lambda and the width needs to be at least 10 lambda. So that's why I'm upgrading that guy from a 10 by 1 to a 20 by 2. So it should perform, or it should have the same performance if we simply double both parts of the aspect ratio. So NMOS. This is MSU3. We have a width of 20. And the gates of these guys are tied together. And then let's see. We're going to have a PMOS current mirror. This is M3 of the startup circuit, and it is a 30 by 2, which we have been implementing as 3 10 by 2s in parallel. So let's continue to do that way. Apply. No. Text, there we go. Just put that down here for now. And I'm going to make a couple of copies of this guy. And make sure everything is named correctly.
Dr. Hartman.
Yes, sir.
For MSU3, I don't think you ever set the spice model.
You are absolutely correct. Thank you for that.
Yep.
So it is, let me select the right thing. There we go. So the SPICE model needs to be set to NMOS. Thank you very much. Or I would have forgotten it, and then when we tried to simulate it, been like, why the hell isn't it working? Need to tie all these gates together, and I may go back, I'm not sure yet, and make that MSU3 2 parallel 10 by 2 NMOSs, but we'll play it by ear for now. So let's go ahead and do M4 while we're at it. And these guys are all in parallel as well. So I'm going to do the exact same thing. There. Okay, so I've made an error here. Because I currently have the drain of MSU3 connected to the drain of M3, and that's not the case. It should be that the drain of MSU3 is connected to the gate. So that's the connection that we should have. All right, so let's put my NMOS transistors down here. So this is a 10 by 2. Oh, that's the wrong model. That's not the 4 terminal. All right, so this is M1, 10 by 2. It is a NMOS. And the gate of this guy is tied to the gate of MSU1. We're going to have a ground connection. And then the drain of this guy is tied to the source of this one, which is tied to the drain of PMOS. And then we also need to tie this down to the gate. All right, then we have our other NMOS. And this is a 40 by 2, so I'm definitely going to make this 4 NMOSs in parallel. So this would be M2A 10 by 2. And B, C, D. Eights. Tie all my sources. All right, so gate of M2 is tied to the gate of M1. The drain of M2 is tied to the drain of M4, which is also tied to the gate. And I need all these drains to be connected. I missed that. Okay. All right, so that topmost thing up there is going to be VDD. I need to tie my sources of my NMOS to ground. So this guy over here, M2, I'm not going to tie the source to ground. I'm going to tie, or the body to ground. I'm going to tie the body to the source instead. And that is, again, purely to avoid body effects. All right, so can anybody see anything I'm missing other than the resistor of this guy?
I think you missed M2D's body connection.
Oh, I did, thank you. All right, and so now I just need my resistor. So I gotta remember where resistors are, Spice. No, those are all sources and stuff. Miscellaneous, no. There we go, resistors. So what kind of resistor am I gonna want here? High res poly 2, since that's what we've been using for all of our resistors, seems like the most logical choice. I'm going to rotate that. Put it here. So let's start with what's in the textbook as 6.5K, and I'm going to leave the width and length at 2x2 for now. We'll fix that later when we figure out exactly what resistance that we need. All right, so I'm going to bring a pin from the gate way out to here. This is where I'm going to export V bias P. So that we can measure what that bias voltage we're generating is. And I don't know that we're going to be using an NMOS bias in our circuit at all. Depends on if we have enough time to get to generating a push-pull output stage. But I'm going to reference it just in case. So this will be V bias N. All right, anybody see anything connected improperly?
I don't see anything.
All right, well, then now we need our spice code. Oh, no, that's wanting me to just give it things. Let's see, miscellaneous, I think. Spice code, there we go. All righty, so for this guy, we need to initialize our voltage VDD. So it is at node VDD for the positive polarity terminal, 0 for the negative polarity terminal. It is a DC source having 5 volts. That's the only voltage that we have in this whole circuit that we want to set. So let's just do a transient analysis for 5 milliseconds and make sure to include the model. Models.txt. Apply. Okay. And let's see. 2 errors. I just want to see what they are. An unnecessary pin. Not particularly concerned about that. And another unnecessary pin. So nothing too scary. So let's add trace of V bias P. And we're getting like 3.6307 volts. So we're looking for something around in the ballpark of 3.88. So that resistor value is pretty close. So I'm going to close this guy out, just go in here and change this to 10K and see what happens. See if I'm heading in the right direction or the wrong direction. Right at 3.8. So heading in the right direction, but still not quite where we need to be. So I'm going to give 15K a whirl. And that seems to work out pretty good. So 15K is the resistor value that we're going to use to generate our 3.88 volt reference voltage for biasing the current mirror that is in turn biasing the differential pair circuit. All right, so everybody able to run that simulation and verify that 15K is giving us the output voltage that we want.
So
If our, go ahead.
no, I was just gonna say mine seems to be flipped. My V bias N's getting the 3 and some change volts. My V bias P is in like the point. It's like in the millivolt range.
All right, let me simulate this again and let's look at what's happening here. We'll check V bias N as well, right? By stack. Add traces, V bias P, and V bias N, because this V bias N should be around 1.2 volts, I think. Oh, or around 1 volt, okay. Yeah, that may, so if V bias N is supposed to be a VTH plus VDS sat above ground. So that would be 0.7 plus roughly 250 millivolts. So somewhere in the range of 0.95. And just for the sake of argument, let's see what we got here. 1.05 volts. So it's about 100 millivolts higher than it really needs to be, but that seems okay. So let me stop sharing real quick and then that's not what I wanted to do. And sharing options. All participants. Okay. All right, so Aiden, are you willing to share your screen so we can troubleshoot stuff?
Yeah.
All right. So one thing that I see is you have dot include, not dot include the right models. That might be something. So let's fix that. And let's run your simulation now and see if that fixed it. And if not, we'll do some further troubleshooting. Nope, still real low. All right. So So you have the body of MSU3 tied to ground. Tie that to the source of MSU3 instead, and let's see what that does. All right. So just to be clear, those NMOSs in the bottom, they have a length of 2.0 and not 20. The ones that okay. Hit cancel. Because the ones on the left, MSU1 and what should be M1.
Mhm.
I can't, I'm just trying to look at your screen. I can't tell if that says 2.0 or 20.
I think they all should be 2.0.
Okay, 2.0. All right. So let's see, you got a 10x2 NMOS down here in the bottom left, where you got a 10x100 PMOS. You got a 20x2 NMOS, 30x2 PMOS, 30x2 PMOS, 40x2 PMOS, 10x2 NMOS, 15K resistor. All right, so now you got all the right sizes. So let's start checking these connections. So the drain of MSU2 is connected to the gate of MSU2, which is connected to the drain of MSU1. So that is correct.
I think I see it. Is it the resistors? I don't think the resistors connected properly.
Maybe you're right. It does look like it just kind of short straight through it. Maybe that's the issue. Yep, there it is.
All right.
Got it.
All right, so not having the resistor at all apparently screws this thing up pretty hard. So, okay, great. Everybody else's seems legit. All right, nobody's saying it isn't. All right,
Can I see your schematic one more time?
sure.
I think I. Okay, yeah. The body of M3C is floating and tied to anything.
3C, you are correct.
Because I had to use a different resistor value, and I didn't know the difference.
All right, so let's see what's what with this. Tools, simulation, right click.
I mean, I just had to use 14K instead of 15.
Okay, so that pulls it up to 3.89. Yeah. All right, so let's back that resistor value off a smidge. And thank you for that catch, Mitchell.
Dr. Harmon, my electric doesn't seem to want to write like a spice file. Like it won't create one. I keep trying to like simulate it, and it's saying that it can't find like the path specified.
Give me just a second, and I will troubleshoot that with you. I want to
Okay.
see if this 14 works. All right, add trace V bias P 3.88. All right, yep. So 14K. All right, Alex, that was who was talking a moment ago, right?
Yeah.
Share your screen, please, sir.
Okay.
Click on the wrench and screwdriver icon.
Where is that at? Sorry. Oh, right here.
Yep.
Okay. Yeah,
Now-
it was. I'm sure it's something wrong with these settings here. That's kind of messed up.
if it's anything that's wrong, it's the path. All right, what it's saying, error opening D downloads.
Yeah, so like it's trying to open like a file whenever shouldn't it be creating one if I haven't like simulated it yet?
I would think so, yeah. What is your path for the run program?
Oh, it's just to my LT Spice. My Spice is installed on my. I have an SSD and a hard drive, and the Spice is installed on my SSD, and then I'm having it output to my hard drive just to not take up a bunch of space.
Right.
Let me. I hadn't made the actual folder. Let me see if this works. That would do it. Okay. Let me make
Putting it
sure.
in a folder that didn't exist. And it didn't.
Yeah, I figured it would make one, but guess not.
All right.
Okay, let me just make sure this works really quickly. I need to fix mine. Okay, oh, I didn't change my resistor value.
We're looking at 14K. Give that a whirl.
Okay, that's the value we're looking for, right? 3.88?
Yeah, so somewhere close to 3.88. All right.
Okay, cool.
So that's looking groovy then. Okay.
Let me stop sharing. There we go.
So then I guess it's time to work on the layout. So go to Explorer, right click, create new cell, name it the same thing, beta multiplier, make a layout, and jump into components. And we're going to start working on this guy. So I'm going to put all my PMOSs up towards the top, starting with MSU2, which is not going to care for this 10. Oops, that doesn't matter. 100. Apply. And we've been rotating all of these guys, right? So that the source and the drain are usually on the left-hand side of things. All right, so this is our big honkin' transistor MSU2. I'm gonna make that text a little larger so it's easier for my old eyes to see. And I'm also going to set my splice model so I don't forget about it. That is not what I wanted to do. P active is going to go over here. All right. So that's that.
No.
It's not that.
Oh, sorry.
No problem.
Didn't realize my mic was on mute.
Not a problem. No, I talk to the computer all the time. Well, you guys hear it. Or I'm like, why won't you work, pen, etc. I'm going to wind up putting all of these PMOS transistors. So this is going to be M3A in one large N well. Set spice model. All right, and I know I'm gonna have an identical one of these, so I'm gonna be lazy and just copy paste it right over here. All right. All right, so let's see, how close can I get these guys? Oh, actually, I haven't checked for errors at all yet, so let's check errors. 4 errors. The notch layer is less than 6. So that is just saying that those two guys are too close together, but if I put some N well between them, everything will be fine. So I'm not worried about that error. talked about that one. Notch layer, same thing. Node metal 1 P active contact is less than 6 away from. So that's saying those two metal layers are too close together. They appear to be significantly larger than 6 units. Just for the sake of argument, I'm going to see what happens if I put in my N well. I need to make sure that it is easy to select. And trying to get it just the right size. There we go. All right, so yep, having that one piece of end well there makes all that work out. So I'm gonna try, let's see, how close can I get? I still need to be able to connect my, I'm trying to think about the connections and all that kind of stuff that I'm gonna have here, because I'm gonna have a connection to VDD up at the top. I'm gonna have to tie these gates together. For my really, really large one, I need room to run that gate drain connection down. That should be pretty easy. So let's see how close I can get these guys without getting an error. So if those touch, that should be fine. So still nothing. Still nothing. Still nothing. Still nothing. There we go. Less than 0.5. So I just need to move these guys to the right. No errors. All right, so that's as close as I can possibly get those two guys. With respect to my 230 by 2 PMOSs, I'm just trying to think about, since I'm going to have a gate, the gates tied together, and then a drain connection. All right, so I guess I'm going to start making my metal connections and see how things go here. So this is going to be my source connection for let's see, this is the source of M3, which is going to get tied to VDD. While I'm at it, let's go ahead and go over here and knock out no errors. the source of no 4. Oh, why are you going to be difficult with me now when you were working so well moments ago? This is the drain of 3. Just to make that text larger. Here is the drain of 4. All right. So the gate of 4 is tied to the drain of 4. I feel strongly that this is going to give me an error, and it does. So it's saying that that little notch between them is smaller than it needs to be. So I'm going to make this, let's try 4 wide for now and make sure it doesn't extend. Let's make it 5. Two errors. Those two metal regions are too close to each other, which will be easily rectified by connecting them. All right, no errors. So that is my gate tied to my drain. Now I need to run all my other gate connections here. And all right, so all those connections are okay. While I'm at it, I'm going to go ahead and make a contact. So this is going to be too close to the source for sure. So how far do I need to move this over before it doesn't give me an error? All right. And so this guy right here is how I'm going to export my signal V by SP. So I'm going to go ahead and select this pin, hit Control E, V by SP. All right. Now let's wire up the gate of this guy. Let me turn my ringer off because my mom is texting me about her Fitbit, which I'm sure you guys are thrilled to hear about, but I'm not. All right, so the gate of transistor M4 is tied to the gate of transistor M3. So what I'm questioning here is, do I want to have a polysilicon run? And I think it'll be okay if I make it a big fat one like this. So I think we made the other one 5. Again, I'm just trying to minimize the number of squares so that we're having the least amount of resistance, so that we shouldn't see any appreciable voltage drops that screw things up too much. Actually, before I do that though, so this is the drain. All right, I want to see if I can move these two guys closer together. Because their drains aren't connected. And I don't think I'm going to have to run anything between them per se. All right, so that's as close as I can get those guys. Okay. You're frustrating me. What I'm trying to do is make this chunk a little. All right. I'll leave it like that. Trying to make it look prettier. Apparently it's not going to happen. Okay. So I have these guys all tied up as tight as they can be. So those are all of my PMOS transistors. I'm trying to think. I'm going to have to jump over my guard ring to connect the drain of all of those transistors to NMOS transistors. And I'm going to have to jump the gate drain connection of my really big one as well. So let me go ahead and establish that. All right. So I put something odd in the middle there. That's the middle. There's this poly run. No, that's exactly not what I want.
What was the size on that on MSU2 again? Was it 10 by 100?
That is correct.
Okay.
So this works. So how tight? All right, so this guy needs to come down one, which means this guy also needs, nope. Two errors. So if I use that wide bit like that, it gives me the error. Let's see, these guys aren't connected. Frustrating thing. Why won't it let me select a node? All right, let's try this again. Two errors. Less than. All right. All right, so I'm getting no errors that way. Will it let me move this guy over? No. if I take this little guy in the middle and I make him 5 with neither end. No errors, okay. So that's the shortest run of poly I can have and still have that work. So that is the gate drain connection, and I'm going to again have to jump that over my guard ring to get to my NMOS transistors. So I might as well go ahead and put in all of my metal 2 to metal 1 connections. Just stack these guys up. So there's one there. I'm going to have to go from metal 1 to metal 2 for my drains. Let's see, no errors. All right, great. All right, so that's going to let me jump over my guard ring and all that kind of good stuff. So now it's time to put the guard ring in. All right, so tools, where's the measurement tools? Could have sworn there was. That's setting my grid size, I'm almost positive.
Is it? Oh, yeah, you see it.
Negative 114. So 200 at least for the links. So that's going to be an end well. And let's make it 210, so we'll overlap. I need to make sure that I have the select thing selected so that I don't just constantly try to measure stuff over and over again.
So would that actual size be 200 lambda?
From the edge, yeah, from the edge of the N well over here where my left hand or where my cursor is, all the way to the edge over here on the right hand side where my cursor now is 200 lambda. But because we're not wiring this transistor to these guys, it's not going to form a 200 lambda long transistor. Was that your question?
Yeah, thank you.
Yeah. So, all right. Actually, I'm gonna make it 220. And the reason why I'm gonna make it 220 is because I feel very strongly that it's not gonna let me get this metal one close to the metal one over here for my bias voltage connection, which, yeah. Let's just measure the height here. Actually, before we do that, 20 errors. All right, so those 20 errors are because this guy is so dang close. So I want to see when I don't have the overlap, or when the N-wells regions are touching, that should get rid of a lot of errors, but not all. There we go. So we went from 20 errors to 1 error just by getting rid of that small sliver of P-well. So it's saying that let's see, less than 12 wide is 11. And that's something that we usually can easily get rid of. All right. So I'm thinking, and we'll measure it and make sure that it's saying that this, oh, that's 12 and a half. Okay. So the error it's giving us right now, I'm measuring from this corner up. So it's saying that this guy right here is 11 wide and it needs to be 12 wide, and that will take care of itself when we put the downward bit. So let's delete that. Oh, goodness. So make a copy of this guy, drop it down here on bottom, move it over so that it hopefully lines up. I'm gonna put a big ol' piece of N-well. Make that easy to select before I forget about it. So there was a chunk of N-well right here. I'm gonna delete that because we move things so close it doesn't matter. I'm gonna make this guy 220 and this guy 24. What I'm hoping let's make it 30 for now. That's going to cover up effectively all of my gaps and will let me play around with how close I can get this bottommost part of my ring to that metal 2 connection before it freaks out. So it's got 2 errors and it says less than 12 wide, but it shouldn't be. Okay. So the issue here, now I have this little stub right here that isn't quite wide enough. So let's make this 224. one more. All right. The smart thing to do would have been just measure one of the long things, but I didn't think to do that until after I had done all that finagling. All right, can I move this guy up? So that guy's exactly how long it needs to be. All right, let's see, measure. Looks like they're 41. All right, so the problem with doing 41 is that they don't align. That's just, all right, so I'm gonna need to make it 45. And I need to make this guy down. This guy up. No errors. So I'm just going to get rid of that little extension thing because I don't care for it. All right. Same thing down here. All right. So I believe I have all of my PMOS transistors taken care of there. So for my NMOSs, I'm going to have two that have a connection to a body connection to the ground, and two that have a body connection to the just to their source. So let's try to think about how I can implement this strategically. All my PMOSs are good, so before I somehow manage to screw this up, I'm going to save my work because it took a while to get that. All right, I'm going to do my 40 by 2 NMOS next. So this is going to be M2A, 10 by 2, rotation 90 degrees. This text rotated and larger. And down. Set my splice model. Loss. Larger and rotated and scooch it up. And I'm going to need 4 of these guys. Since it's NMOS, I'm going to have N active. Inactive. Oh, didn't change the name. Oh. Okay, let's see. All right, so that's my 40 by 20. So what I'm currently contemplating is instead of putting a single ring around transistor M2 and transistor MSU3, So putting a ring around those two guys that don't have their bodies attached to ground. I'm thinking about putting an individual ring around them. And the reason why I'm considering that is because the source of MSU3 is at the gate voltage of transistor M2. It's at the same potential as the gate voltage for transistor M2, but the body, but the gate voltage for M2 is not the same as the source potential for M2. And so I don't think I want them to have the same body potential. Does that make sense?
I think so, yeah.
Yeah, so effectively, if I put them all in one ring and let that potential float to be kind of whatever it needs to be, that would be raising the body potential of M2 up to the gate potential, which will give me body effects. So I'm going to put a ring around this guy after I wire it correctly. All right, so let's see. So which do I want to be my drain and which do I want to be my source? No, stop being difficult. All right. It's frustrated me enough, so I'm just going to do it the easy way. Put a metal piece out there, connect from that to this. Oh, you difficult piece of junk. There we go. Oh, goodness, no. All right, so this guy is going to be my drain. What am I doing? Here we go. Drain of transistor 2. Oh, let's make that text larger. And in turn, this guy down here is going to be my source. All right. The gate of M2 is going to be tied off elsewhere. Oh, what did I just do here? There we go. It's going to have to jump over a guard ring, so that means I'm going to need to do something similar to what I did with that PMOS transistor up top, I think. Let's see, the drain source is going to be tied to our resistor. And gate voltage is going to be tied to V bias P. So let me look at what I did over here. All right, that's what I thought. So I'm going to put a contact over here. And I'm just going to move this guy until it doesn't give me an error. No error there with it in the corner of that. All right. So that is where I am exporting V bias N. So click on the pin. Now I'm going to tie my gate together, serpentine style. And this gate voltage is going to have to jump over a guard ring. So I'm going to have a similar thing over here. All right, no errors. That is odd, in my opinion. Let me see if this. I don't know why these two are 0.172 too close, but this guy and like this guy on the right hand side and this contact on the right hand side aren't, because this thing is supposedly a 100% mirror image. That's odd, but oh well. Oh, that one's down lower, that's why. Okay. Now we're good. All right, so we have our gate taken care of, sources and drains and all that kind of good stuff. So let's put a ring around this. So I'm going to move it away from that one for a second. We're going to measure from here. $53.5 at 20. So let's try 70. That would be a P well connection. No errors. No errors. No errors. Closer here. All right. So that's as close as that guy can be. No errors, no errors, errors. That's as close as that guy can be. Measure here to here. 38, so let's call it 40. These guys aren't quite lined up. No errors. No errors. All right. So our source should be tied to our body. Let's see what happens. It's 4. Okay. All right, let me think about what's going on here now, just so I'm above board with everything. So my drain is going to have to jump over the guard ring and connect to transistor M4.
So do we not need like an end well region to cover up the little gaps because it's not giving us an error, or like is it necessary? I guess is the question.
So for this, it's actually a P-well region that
Or,
we,
sorry, yeah.
and the reason why it's not giving us an error like it does when we do the N-well region is because the substrate is also a P-well region. So we could put one in there. So we could specify one, and it's not remotely a bad idea to do that, because we could use this design potentially for a not C5 process by doing things like that. So to be clear here, put in a P-well node, and let's see, make it easy to select so I can move it if I need to. Let's do some measurements real quick. So from here to down here, 45.5 and 76. Nope. Did I not make it easy to select? P-well. Pure P-well. Pure P-well node. Why is it being dumb? Oh my goodness. All right. There we go. What was the distance in the Y direction that we measured?
I think it was like 35 or somewhere around there. Well, I'm not entirely sure. It should be around like 35 or 40 though.
So, yeah, so I just put a big chunk of P-well effectively covering underneath this entire transistor thing. But the reason why it doesn't give us an error is this gray thing with no lines over it is also P-well. In this particular process. And we had that set up when we went through some of the options. I can't remember exactly when that was, but it was a while back. So I'm going to slide this whole guy over here. And I think as long as the N well and the P well aren't touching, I shouldn't get any errors. Let's find out. No errors. Okay. So what I need now is I need to connect my drain from transistor 4 to the drain of transistor 2. So I've got this metal 2 run that I have making it, oh, I shouldn't have done that. I should have just, no, I gotta make sure that this is all hunky-dory. And it's definitely not going to be like that. So I need it to be giving me metal 2. All right, let me take this guy and move it out of the way for a second. Making it 5 by, no. Is that the same size? Yeah, I guess it just didn't look like the same size to me. So I'm going to take this guy and I'm going to move it down here. Tie it to this metal. No error. I'm not sure why I have that stub of metal there. So just so I make sure I don't delete something I'm not supposed to delete. Oh, stop being dumb.
Dr. Hartman,
Yes.
can you remind me why we put the transistors like I'm going to say vertically instead of putting them all, say, horizontally and connecting them?
So are you asking if there'd be any difference if I rotated this entire thing 90 degrees?
No. Do you mind if I share my screen just for a sec?
Go for it.
Um,
Because I'm not sure that I'm understanding your question.
right. Like this. Do you see?
Right. So, so those are 3 transistors in parallel, you're saying? Because the drain is attached, the sources are attached, and the gates are attached. It's physically larger.
Okay.
Really, I mean, run your error check. 0?
Yeah, I'm not running any errors, but oh, I am. Never mind.
So what do the errors say? So click in the top window, hit F5, and now hit OK.
So it's just all spacing stuff.
Yeah, but so it's saying that those active regions are too close to each other and all that kind of stuff. So you'd have to spread them out wider, which would then
Okay,
more physical space up and all that kind of jazz.
cool. I was just wondering. I couldn't remember.
Yeah, I'm just trying to make things as small as possible because generally speaking, space is at a premium. All right, so now let me get back to trying to figure out how to connect this. Stop giving it to me on.
I think it's because you found it. It's because you had the middle one selected.
Back this guy down. And I want to make sure that I don't have that little stub of metal 1 underneath because it's going to cause it to likely freak out. All right, so that is the drain connection. I mean, that's metal. Let's see, it's 30 by 4, so that's 7.5 squares. Probably 7 squares. So that's on the order of like 1 ohm of loss resistance between those 2 points. What I'm trying to think is if I wanted to instead make multiple connections in parallel to lower that resistance, or just make one large wide connection to go across there. I know it might sound silly, but I'm trying to minimize the losses here. Like 1 ohm isn't a whole heck of a lot of resistance in a macro scale circuit, but in a micro scale circuit, it might be. I'll leave that as it is for now. I'm going to put this guy back where it needs to be. All right, so it's 9:49. So that's enough for today. So on Thursday, we'll finish up the transistor MSU1, MSU3, and M1. Try to get everything finished up in our layout, run some simulations to make sure our bias circuit is working, then connect our bias circuit to our current mirror, make sure that the current mirror is working, then connect everything to our differential amplifier, and hopefully everything will continue to be working. And I imagine that'll probably take the majority of class on Thursday. We do have another test coming up. What that test is going to be is I'm going to give you guys a schematic for some basic kind of, MOSFET amplifier building blocks. So, common source, common gate kind of thing, and just have you do a schematic and layout of them and make sure it simulates correctly. And we'll call that exam 2. Anybody have any problem with that?
Sounds good.
All right. And then let's see. Next week is the last week of classes. So hopefully, we're finishing up this week by getting our bias circuit and everything connected. So what we'll do next week is hopefully be able to put a gain stage or 2 on the output end of our differential amplifier to boost our voltage gain. And then we'll have an op amp. I mean, technically we kind of already do, but we'll have a slightly better op amp. So that'll be something. All right, so I'll see you guys next Thursday, or 2 days from today, so next Thursday.
Dr. Hartman,
Yes, sir.
you'll be in your office hours tomorrow around 9, 10 o'clock?
9 o'clock, I have a couple of Circuits 1 students coming to harass me about things.
Okay.
So 10 may be better for my schedule.
Okay, perfect.
All righty, see you at 10.
All right,
Dr.
bye.
Hart, one more thing.
Dr. Hartman, for the mock FE exam today, is it just online or what's
Yeah.
going on with that?
So for those of you that are in senior design right now, while I'm sharing my screen, let's look at what's going on. So we go into Moodle, and my internet is slow because of course it is. My courses. Go to the Meta ELEN 406 page, and I have created a little place that says mock FE there. Click on it. It has the NCEES handbook, which you're allowed to use, and it also has the mock FE itself. When you click on this, it's going to ask you for a password, and I will be sending out the password, or Dr. Vittorio will be sending out the password using the Moodle page, probably a little bit closer to the test. You have until midnight tonight to finish it. You have 2 hours to complete your attempt. So you don't have to do it exactly at 2, although you should have a 3-hour window of time open at that point because you're scheduled to have a class at that time. So anywho, did that answer your questions?
Yeah. So we'll be meeting next week for senior design to like talk about progress and stuff like that. So no meeting this week, basically.
Yeah. So no physical meeting this week. Next week would be your presentations, actually, right?
Right. Okay.
So we're kind of running up against the wall there. I'm working on getting the papers and all that kind of stuff graded so that I can get them to you within the next day or so that you can have feedback and work on refinements over the next week and a half.
Okay, good deal. Yeah, that was my just wondering when we get the papers back. So, but sounds good. All right.
My lazy ass, which is today.
Okay, sounds good. Thanks.
All right. Catch you later, Alex. Thank you.
Have a good one.
You too. Any other questions before I close this here Zoom meeting? All right, catch you guys later.